My name is Ryan Talbom. I'm in Group 3, and this is our presentation on cjdns. So before we get too far into it, something to keep in mind. The authors of cjdns and the people who make networks that rely on it seem to always have this in the back of their head. But the original intent of the internet as kind of a network of networks to provide open access to information and increase communication between different groups of people and the people using these interconnected computer networks. This is kind of their overarching goal. This is what people seem to always be thinking of as they do this kind of thing. So the goal is to make it easier to connect, make it more resilient, and preserve the integrity of the data that's actually going across this network. So some problems with the internet as it currently exists, too many clients, especially now that we're talking about Internet of Things and we've run out of IPv4 addresses. There's just not much namespace left for much of anything. So too many clients is definitely a big one. You hear about that in the news and things like that. A lack of privacy. A lot of what this is built on top of is quite old. So I mean, IPv4 really has no encryption or anything like that to protect the content that's in there. There are proposals to do it, like IPsec, and it has been done in some cases, but it hasn't really gained widespread adoption. And then lastly, our core routers have quite a burden of things to remember. The routing tables are getting really large. It seems every day you read about something else going wrong with Border Gateway Protocol. It's a protocol that's built on trusting the routing information from people around you, which isn't necessarily the way things work nowadays. So it's continually plays catch up. Some possible solutions to this. You could use IPv6 by design. What they always tell you is there's enough IPv6 addresses as there are grains of sand on Earth. That's what they say. 128 bits, you've got a lot of room to work with. And when you're using that, you don't need network address translation. Okay, you don't have to all hide behind one IP address. Now you do have to rethink things like firewalls and stuff like that that people may have forgotten, but you can all be internet facing. One cool thing that you can do with this that cjdns does is you can embed a hash of the public key in your actual address. So it uses this address space, FC00/8, and what it does is it does an SHA-512 of an SHA-512 of the public key, takes the first 16 bytes and puts that here as the address. And it makes sure that it starts with FC. It brute forces that. It does the hash over and over until it gets one that works. All right. You can also utilize a mesh of peers. The mesh by default is a resilient structure. So if you had, say, 4 nodes, and every node is connected to every other node, if something bad happens to one of these nodes, you can still route your traffic basically where it needs to go. All right. The cost of doing this is it's not going to be as efficient, for one, and two, in the case of this type of network, you're going to need peers to connect to. So you can connect to public peers, or even better, you have friends that are geographically close that you communicate with that are running this too. You connect basically through them. And then the cool thing is, once you've got all these peers set up, you can use a distributed hash table for storing this routing information. So everybody can share the burden of routing. And DHTs have proven feasible and popular. If you look at like Mainline on BitTorrent, things like that. It's shown that it can work and it can store information, right? Even with a decent amount of churn, which is impressive. Clients coming in and out of the swarm in the case of BitTorrent. All right, so it can be built on layer 3. In this particular case, it runs over a UDP port on top of IPv4, and then later on you can deal with the lower layers. So for now we can gain adoption because we're using this existing structure, but later on if we want to, we can use some other cool ways of connecting devices. If you're a radio person like me, you can look at some of the neater radio protocols you can use to connect devices. Then this will just pick up from layer 3 on up, basically. So cjdns has 3 main components. It has the switch, the router, and crypto auth, and they all work with each other. Right? You can't really think of it like layers at this point because the switch may get something from crypto-auth and it may get something from the router. They're all kind of working in this big cycle in order to make it happen. What I'm going to do is I'm going to take you through how the switch works, the router, and crypto-auth, basically through all of those, and show you basically how it works. All right, so inside the switch, first off, everybody on the network is going to have a switch. The switch determines which interface to send something through, depending on the directors that you find inside the route label. Directors are just a sequence of bits. Interfaces are connections that you have through crypto-auth to other nodes in the network. So for example, if switch 1 wanted to send something to switch 3, it would build a route label that looks like this. Let's see. I want to get there, and I want to get from here to there, and I want to get from here to there, right? And what this route label does is whichever switch you're in, it's going to try to match a director. And then it's going to shift those bits off and push it out the interface. So we start in switch 1. Switch 1's going to match this director and say, oh, okay, that's my director to get to switch 2. Let me shift these guys off and send you out to switch 2. All right? And switch 2 is going to look at this and say, okay, that's my director to get to switch 3. Shift these guys off, send you out to switch 3. Switch 3 is going to say, oh, that's my self director. This packet is meant for me. And switch 3 is going to give the packet to itself and deal with it. Now, the whole time you're doing this, what you're also doing is you are tracking how to get back if you need to. So right here, if we look at the switch 2 step, when switch 2 pushes this thing off, it could also add something for getting back to switch 1, in this case, this one right here, in reverse on the front of this label. All right? And then as you build that up, if something goes wrong, you take the whole route label, you reverse it, and you've instantly got a path in order to be able to get back home. One important thing to note about this is that the only people that know the IPv4, in this case, address that we're using to connect to each other, are your peers that you're peering with to connect with. Everything else goes through these directors. So if you intercepted one of these packets, one, you don't know the width of the directors, so it's going to look a lot like gobbledygook. But if you had some more information, you might be able to figure part of that out. You're still not going to know physically where the different nodes are located. All right, so it does provide for that. So the switch is basically picking interfaces and pushing things out through those interfaces. The router is interesting. The router runs a distributed hash table, and every node inside the distributed hash table is responsible for remembering about 130 other nodes and the route labels for the switch in order to be able to get to them. So if you've never worked with the DHT before, the diagram you'll see looks a lot like this. Now let's assume these folks are close to each other, right? You keep track of information about the folks that are close to you, and maybe you keep track of that one. But you don't have to keep track of information on these folks over here, right? This person keeps track of information about the people that are close to them, but it doesn't necessarily have to keep track of this over here. When you are trying to discover the route label in order to be able to get to something, what you're going to do is you're going to look at everybody you keep information on, and you're going to look for whoever is closest to where you're trying to get. The person who's closest, you will send out a query to them, and they will respond either by telling you, one, how to get there, maybe it's a one-hopper, or two, they'll say, hey, here's a node that'll get you even closer. The metric used to determine this closeness is based on the Catamiglia one, which is just a simple XOR. But if you'll remember, our IPv6 addresses always start with that FC prefix. So we also throw in here a rotation by 64 bits, just to prevent collisions and things like that. So this will tell you how close you are to another node. You will basically maintain a list of nodes that are close to you, and you will have these router messages to determine what the route labels are to get you from one to the other. Router messages skip the whole routing protocol. They are just sent UDP source port 0, destination port 0, right to the node that you are trying to query. All right? And then this information is passed back and forth using B-encoded dictionaries. If you're not familiar with B-encoding, it's another way of representing data like JSON or XML or anything else. Became really popular with BitTorrent, which is probably why it's used in a distributed hash table. All right? And your goal is to build up a route label in order to get you to one of these other things, everybody keeping track of about 130 nodes that are close to them. All right? That just leaves us with CryptoAuth. CryptoAuth is the wrapper that we use to make sure that our connections over interfaces are encrypted. It's got 3 types of what they call handshake packets, and then it's got data packets. So basically, you will send out a connect to me packet. And inside this packet, you will have your public key. All right? You'll have a permanent public key. Okay? Then this hello packet will come back to you. The hello packet will have the permanent public key of who you're trying to talk to, as well as a temporary public key of who you're trying to talk to. So now they can communicate with you by encrypting things using your permanent public key, which they do in this hello packet. And from now on, you can communicate with them by using either their permanent public key or their temporary public key. So you'll respond, usually encrypted using their temporary public key, and this key packet will contain your temporary public key. So what we've done here is we have exchanged a temporary public key so that the keys are constantly changing. So if something happens with the permanent public key, you've really only cracked the beginning of this handshake protocol, right? The point of swapping keys is it makes it so that if you crack one of them, you still have this randomly generated temporary public key that we're using for this particular session. Once that key exchange has happened, connect to me, hello, key packet, each side knows how to talk to each other, the data packets start coming back across. Right? The data packets have some interesting parts to them. They use a nonce in them so that you can make sure that they're in order, and you can make sure that they are related to what you sent out, so you can avoid replay attacks. Right? And on this side, the official client actually implements a sliding window protocol that makes sure that those data packets are within its window. There are no acknowledgements, so what will happen if something's outside of the window is it'll basically just get dropped. Right? So it's a pretty simple protocol. The part that's not so simple is the encryption. It uses Daniel J. Bernstein's, what does he call it, libsalt, I think, NaCl. It uses that in order to be able to actually facilitate all this encrypted. All right, and as you'll see, the switch uses this CryptoAuth, and the router also uses this CryptoAuth. All right, so coming up next, we have a screencast demo of an actual node that is running CJB DNS.
Okay, as promised, we're going to do a live demo of a node that's actually running cjdns. So I'm just changing back into my home directory so we can get started here. But this is a server that's currently running in Chicago, I believe, that is connected to the Hyperborea network using cjdns. I'm going to show you how it's set up. So the version of cjdns is the stable branch pulled from Git, compiled from source. And it's currently using this config file here. I want to point out some things about this configuration file that are important. All right, here in the interfaces section, you'll see that we have a UDP interface, and you'll see a collection of the peers that we are actually going to connect to. Now, these are all public nodes, and you'll notice that for one of these public nodes, you have an IP address and a port number, and you also have a password in order to be able to connect to them. All right, and remember, this is running UDP over top of IPv4 connected through these peers. So peering is an important part of the network. It's referred to as a network of friends. in a perfect world, you'll peer with people that you're actually geographically close to and people that you know. Because basically you're sharing bandwidth amongst yourselves. You want to have that kind of connection. So in order to be able to get connected to the network, you either have to use public peers, which aren't always up and don't always work so good, or you have to have made some friends in order to be able to connect to other people that are currently on Hyperborea. You'll see down here, these are my my IPv6 public peers are listed down here. So CJD route is currently running in the background. There you see it. It's got a process ID of 8348. And what that has done is that's actually made a new interface. So if we look on here, we've got this ton1 interface. It's kind of interesting to look at. First thing you notice is that it's not encapsulating anything, right? And it's got a hardware address of straight zeros. But this IPv6 address is important. First off, it has to start with FC, which we talked about before and we addressed. And this address is the SHA 512 hash done twice of whatever our public key is, the top 16 bytes of that. Right? It tells you a little bit about how much we've received, how much we've transmitted, and basically anything that gets put into that interface is going to be picked up by the CJD route daemon running in the background. And likewise, it's going to handle giving stuff back to us. So anything that uses a typical sockets connection or something like that can now work basically through this interface. So one of the goals of cjdns is to make it so that mesh networking just kind of works out of the box. And this is certainly a good way to do that. Some other things you're going to notice is if we look at our IPv6 routes, right, we've got anything going to FC00::/8 is going to go through this ton1 interface. So we've got that set up for our traffic. And then everything else we're going to find out about it, we really can find out from the daemon that's running in the background. Now, the source code actually comes with a really good set of tools. There's a bunch of tools in this directory. They're all written in Node.js. There's a lot of other ways things are set up. You've got Python, you got some stuff just written in Bash, some stuff for Perl, but they're all doing the same thing. They're all going to connect with the admin RPC interface over UDP, connected to the local host running on port 11234. All right, so that's basically running in the background, and you can find information from the currently running daemon. So in this case, the first thing I want to know is I want to know a little bit about my peers. So I'm going to run, let's see, Node.js. I'm going to run this peer stats, and this shows me who I'm connected to. These people make up my connection to the Hyperborea network. Right, so these are the people who will actually know my IP, not just my IPv6 address on Hyperborea. They actually know my IP in order to be able to connect to me, and they've been gracious enough to allow me to connect to them. Once again, these are the people that you want to be geographically close to. Some information here. You can see this is an IPv6 address. It's got the port number you're connected to. It's got the version that one's running. And then these 8 bytes here are the route label that you use. Sorry, from here to here is the route label that you use in order to be able to get to them. This right here is the public address. From this public key. From this public key, you could derive what the IPv6 address is. If you SHA 512 this twice and took the first 16 bits, it should start with FC and then be a valid address to reach out to this person. And it's got your friendly name over here, and it tells you what status it is. This would be the status as reported by the CryptoAuth connection. Right now it's unresponsive. So this particular peer isn't connecting to us, neither is the next one. But we've got at least 3 established connections here. And you can see it'll tell you how many kilobits per second you got going in and going out on those particular ones. All right. Also of interest, so that's how we are connected to Hyperborea via cjdns. We're also, as a member of the network, we're responsible for keeping information on other nodes that are close to us. And when I say close to us, I mean close to us in terms of the DHT. So remember, a distributed hash table is going to have a metric that it uses to determine closeness. In our case, the metric is XOR, just like Catamiglia, then followed by a rotation of 64 bits, just because the top part of our address doesn't change, because it always starts with that FC. So we want to try to avoid collisions with our hash. So over here you can see same kind of setup. These are all the nodes we know about. It tells you what version they're running. It gives you the route label to get to them. In this case, this is our self interface. So this is us. This is the route label to get to ourselves. It gives you the private key. It tells you when they were last pinged. It gives you a metric that tells you, basically how easy it is to get to them from where we currently are. And what's going to happen is, as people are trying to push packets out to other people, they're going to query nodes to find out what kind of route label they have to use to get there. It's our responsibility to keep track of these 131 right now nodes that are close to us as per the metric. Now, obviously, you're going to have some churn in your network, so you're going to want to have a little bit of redundancy. So I may not be the only person keeping track of these other people. I'm sure that other people are. The bigger this table gets, the fewer hops you have to take to actually track down someone, but also the more you have to keep track of for each part of node on the network. Unlike some of the issues we have with IP and BGP, with routing tables just getting bigger and bigger and bigger as time goes by, I'm only going to be responsible for this 130 or so other nodes. All right, so those are our peers that we are connected to. The last thing I want to show you while I'm doing this live demo is I want to show you some packets actually getting out over the Hyperborea network. So if I do, let's see, let me look up, I'm going to look up this irc.fc00.io, and I'm going to get an IPv6 address that I know is on Hyperborea. So this address here that I've highlighted, this is an IRC server that if you ever actually want to talk to some people about how this works, you can sign into this IRC server. There seems to be a pretty active developer group on there. I mean, there was 90 people in the cjdns room last time I was on there, and they were happy to answer questions, which I really appreciate. Anyway, so let me first make sure that we're going through excuse me, the correct interface. So I'm going to do IP route get, and all right, so this is basically telling you, if you haven't used the IP command before, IP route get is going to tell you how would you get to this particular address, what would you use, and the feedback we're getting is we would go through ton1, which is good. That's what we want. And then we're going to do a ping 6 of that, no, not ton1. We'll do a ping 6 of that actual address and see if we can push some packets to it. And there we go. Packets going across the cjdns network. So while this is pinging, we'll talk about what's actually happening here. So we are using cjdns. I'm going to stop pinging actually because it's annoying me. We are using cjdns in order to look up a route label to be able to get to this address. Once we've got that route label, we know how to put it on our packets so that we can get there. The whole thing is running with that crypto auth interface to make sure that things we send end to end are encrypted. And that's really basically all of it in a nutshell. There are some, I'll show you one more tool while I'm in here that I found kind of interesting. This trace route tool is pretty cool. What this lets you do is it'll show you, maybe I won't show you. There you go. All right, so what this trace route tool is going to show you is it's going to show you how we built that route label in order to be able to get to this address. So you'll see our route label started with just us. All right, that's our self interface. And then we found another node that claims they could get to this original address that we put in there, and it looks like it actually only took 2 nodes in order to be able to get there. So we put out a query. They said reach out to this node. We reached out to this node. We ended up adding their director to the end of our route label, and now we can route packets to that particular address. All right. Thank you very much for your attention.